Hi, my name is Nikolai Polyarny. I am from Agisoft, and I will present a paper out of core surface reconstruction via global TGV minimization. Our goal was to implement a method of polygonal surface reconstruction from given photogrammetric or LiDAR depth maps. The main research interest was to make it applicable on any computer with any operative memory size, even for large datasets. We wanted to develop an out-of-core method so that peak operative memory usage is small independently of the number of photos. For example, this allowed us to process 27,000 photos and reconstruct a 3D model of Copenhagen city with more than 7 billion triangles. It was possible on an affordable computer with 16 gigabytes of operative memory with a big memory usage of 14 gigabytes. We base our method on previous works that used variation minimization. The main idea is to use an indicator field as a scene space representation. It will be -1 in interior space, +1 in exterior space, and 0 on the reconstructed surface. The resulting surface can be extracted into triangles with the Martian cubes algorithm. But in order to find the most plausible indicator field based on depth maps, we first need to discretize our scene space. For this, we need to build an octree. And for the sake of the out-of-core property, we process each depth map independently, creating its own octree in the form of a file with certain Morton codes. Then, to transform these separate octrees into the global one, we combine them using out-of-core k-weight merge sort with the elimination of duplicate Morton codes. That is, we eliminate duplicate voxels. Now the octree needs to be balanced. It is impossible to do so over the entire octree at once due to its huge size. Therefore, it is necessary to split the file that stores the global octree into small parts in the form of the sorted Morton codes. Then, it becomes possible to balance each of these octree parts independently in an out-of-core fashion. After that, by applying out-of-core k-weight merge sort once again, we combine this balanced octree into a balanced global octree. Now we need to build some high-level representation of the scene space so that later we can process it in parts. Let us estimate for each node of an octree the number of cubes in its subtree, and then we can select such a tree top that its leaves will contain at most n cubes. N is selected so that each subsequent processing step used less than 16 gigabytes of RAM. In result, all the elements of one leaf of the treetop are located on the disk sequentially due to the Morton codes. They define the Z-curve so that it enters and exits each leaf of the treetop exactly once. And this means that if we find the first cube from the treetop's leaf on the disk, all the other cubes of this leaf will be located sequentially following it, which gives us a good pattern of input-output access to the disk and greatly speeds up the algorithm. Now, for the sake of the out-of-core property, we can process the scene space part by part in an I/O-friendly style by processing no more than octree cubes at a time. In further minimization iterations, it is beneficial to work with compact histograms of octree voxels instead of depth maps. They can be converted by projecting each voxel into a depth map to add the void of that depth map into the corresponding histogram bin of the cube. For example, the depth map voids for the +1 if the voxel is in the path of the ray, and voids for the -1 if the cube is just under the surface. Since this stage requires a lot of computations, we speed it up with video cards through the OpenCL API. Then we perform the numerical minimization of the indicator function in the same out-of-core fashion, processing each leaf of the treetop independently. The iterative numerical method is also computation bound, so we implemented it on video cards too. Also, we accelerated the convergence with the coarse-to-fine scheme. In order to prevent seams from appearing on the border between adjacent leaves of the treetop, we freeze the neighboring voxels indicator function, which was upscaled from the previous level of the coarse-to-fine scheme. From the resulting indicator field, we can extract the polygonal surface by the Martian cubes algorithm. The resulting method works out of core, is fast due to the GPU acceleration, and I/O-friendly disk access can be run on a cluster and can also process depth maps obtained from LiDAR scanners. Also, the reconstruction adapts to resolution scale diversity, filters noise well, and produces seamless surface. Compared to previous methods, our method is much faster with comparable or better reconstruction quality. Thanks for listening.